But let's move to the next speaker, Andy Skemer from UC Santa Cruz, who's going to talk to us about spectra of young planets. Andy Dunn's doing the timer for you, so please pin her for the timekeeping, and the floor is all yours.
Okay, thank you very much. Yeah, so I'm going to be talking about spectroscopy of young planets, and in particular, I'm going to be talking about directly imaged planets. So Trevor just did a nice job explaining at the beginning of his talk some of the difficulties of doing transits on younger objects. Conversely, for direct imaging, it's actually easier for us to work on younger objects. And in fact, an important point I want to make right at the beginning is that every planet we've ever directly imaged is young. So if you look at this plot, the x-axis shows age, the y-axis shows temperature, which is kind of like brightness, and then the colors are the different masses. So anything lower than 14 Jupiter mass is sometimes considered to be the boundary line between brown dwarfs and bona fide exoplanets. So the bona fide exoplanets are these bottom 5 colors right here. And what happens is that if you have a planet form and it's far enough away from its star so that it's not being heated by its star, it's self-luminous, it starts out with a lot of initial energy, and then it slowly radiates that energy away over time. And because it doesn't have internal fusion, it just slowly gets colder and colder and colder. So when you get cold enough, they become hard to image. A 500 Kelvin planet is very, very faint. And so our very, very best exoplanet imaging instruments, the coldest exoplanet we've ever imaged so far is about 500 Kelvin. And so if you just look at this plot and you see, the most massive planet hits 500 Kelvin at about a gig-a-year. So what that means is that we've never directly imaged planets that are older than a gig-a-year. The reason I'm saying this is because a lot of the science that you want to do is saying, hey, how do planets change as they get older? How does something that is a 1500 Kelvin object look different when it's older? And the way that we do this is by comparing young exoplanets, fairly low mass gas giant exoplanets, to much more massive, older brown dwarfs. And that's okay because they have they're all about the size of Jupiter. They're all about the same composition. The brown dwarfs, sometimes they're around a star, sometimes they're free floating. But I just wanted to make that point. Okay, so the first thing I'd like to do is tell you a little bit about how you take spectra of exoplanets. Now, most of you, if you've done spectroscopy before, the most common way is to use a slit spectrograph. So in that case, you put your object into a slit, and then you use either a prism or a grating to disperse that into a spectrum. What I've shown here is a point spread function in the slit, and you'll see it's a little bit off-centered, which is what happens in real life when you try to put something into a slit. So that actually becomes a problem when we're doing exoplanet imaging with adaptive optics. When you use adaptive optics, you hopefully reach the diffraction limit, and the size of your point spread function goes as lambda over d. So there's a chromatic effect there. But also the performance of the adaptive optics system, how well you're correcting and making that, also varies with wavelengths. So you do better at longer wavelengths. So what that means is that when you put your object in the slit, you are losing light as a function of wavelength. You have chromatic slit losses. And the way that you would do calibrations of your spectroscopy are you put your planet in the slit, and then a couple hours later, you put a star in the slit to do your calibrations. If you put both exactly in the center, then you'll have chromatic slit losses, but they'll calibrate out. The problem is that you might not put your exoplanet exactly in the center. And because it's so faint, you can't see it when you're trying to put it in the center in most cases. So you might be a little bit misaligned with the planet and less misaligned from the star, and you'll never know it. So as a result, it's really hard to do normal slit spectroscopy on directly imaged planets, at least if you're trying to measure sort of the shape of the spectral energy distribution. In some cases, people are doing high resolution spectroscopy where you're trying to see very sharp features, and that still works fine with slit spectroscopy. But my point here is that most exoplanet imaging is not done with slit spectroscopy because of this problem with adaptive optics and chromatic slit losses. So what's much more common in exoplanet imaging is to use an integral field spectrograph. with integral field spectrographs, you get a spectrum of every pixel, or conversely, you get an image at every wavelength. And so this is real data from the Gemini Planet Imager, and it's the discovery of a new planet 51 Area B. And what you can see is there are a lot of these sort of speckle residuals from the star itself, but one of those speckles has a spectrum on the right that looks like an exoplanet. And by look like an exoplanet, I mean it has methane absorption right here and the star does not. And so integral field spectrographs can actually help you find planets because you see a dot and you're not sure whether it's a stellar speckle or a planet. This helps you figure that out. But it's also, it gives you a spectrum at the same time. And so that's the technique that people usually use to obtain spectra of exoplanets. Here's how an integral field spectrograph works. So you make an image, say that's your point spread function of your planet or your star, and you make that image, but instead of putting it on a detector, you image it onto a 2D array of lenses, or a lenslet array. And that lenslet array focuses, each lenslet focuses into a little spot. And then you put in a prism and you orient the prism at exactly the right angle so that these spectra don't overlap. And now you've got a spectrum of every pixel, which is the goal. Here's what this looks like on an actual object. So here is Io, a moon of Jupiter. And if you take sort of the bottom of each one of these spectra, that's 2.8 microns, and you can make an image of that. Then you can work your way up and make images at every wavelength. And here's what this looks like after post-processing. You get the image at every wavelength, and we're seeing reflected sunlight at the shorter wavelengths and a volcano turning on at the longer wavelengths. Okay, so that's how we generally take spectra of directly imaged exoplanets. In my longer talk, I do talk about other ways of doing it and all sorts of different instruments that people use to take spectra of exoplanets. But in this condensed talk, I'm going to get into talking about the properties of directly imaged planets. Okay, so the first thing that you can learn right when you find a new planet is you can just look at how hot it is, how luminous it is, and that tells you something about how planets form and evolve. So if you look at these plots, I've got age on the x-axis, and then either luminosity or temperature or radius on the y-axis. And there's sort of two edge case models for planet formation. If you form by gravitational instability, you likely form pretty hot, and then you cool off over time. If you form by core accretion, after a massive accretion event, you start out a little bit colder. And so if you find a planet and it's 2000 Kelvin, it probably formed by gravitational instability and not core accretion. If you find a planet that's more like 500 Kelvin, it's a little less sure which one it is. But this is sort of the first order thing that you can learn about exoplanets, specifically if you're looking at the young ones. The next pretty straightforward thing to learn, and I'm showing this to you in photometry space, but you can learn more in spectroscopy. It's just easier to show it this way. And so I'm showing a color magnitude diagram here. And these are a population of brown dwarfs. I haven't plotted the planets yet. And so as these brown dwarfs slowly cool off over time, they get a little bit redder and fainter, and then they cross over and become bluer again. And so what we think is going on is that there are these clouds that are sort of sinking, or they're becoming thicker, and they eventually sink below the photosphere. So at the top, you're getting cloudier and cloudier as you cool. And then there's a sudden transition where the clouds sink below the photosphere, and then you have clear atmospheres. So we've done that with a whole bunch of older, more massive brown dwarfs. And a lot of the first set of exoplanets we found, again, these are younger objects, ended up in a different part of the parameter space. And so it appears that young exoplanets hold on to their clouds a little bit longer than the field brown dwarfs. That's also true for the young brown dwarfs that we know about. They can hold on to their clouds a little bit longer. Okay, another thing you can do with spectra is measure molecular abundances. And so here I'm showing a bunch of older brown dwarfs and then younger objects from 3 to 4 microns. And what you can see is that below about 15, so at 1700 Kelvin, there's not much of a feature here, but below about 1500 Kelvin, you get this huge absorption feature, which is due to methane. So that's what we expect to see in giant balls of gas that are colder than 1500 Kelvin. But actually, if you look at younger objects, they seem to lack methane at even these colder temperatures like 1200, which would be down here. So it does appear that the chemistry of young versus old objects is different. We think this is due to non-equilibrium chemistry. So non-equilibrium in equilibrium chemistry, you've got cold gas at the top of your planet, warmer gas as you go deeper in. The chemical reaction between methane and CO favors methane at the colder, higher altitudes and CO deeper in. But if there's turbulent mixing in the atmosphere, some of that carbon monoxide is going to get mixed up into the photosphere. And that happens on a faster time scale than the carbon monoxide can be turned into methane. So that's what non-equilibrium chemistry is. And we see that very commonly in the young objects. Once you can measure the molecular compositions of planets, it's pretty straightforward to measure the atomic compositions of planets. So one thing that has come up before in the Sagan workshop is C to O ratios. If you can measure water, carbon monoxide, and methane, those are your main carbon and oxygen bearing species in these exoplanets. So you measure those three, and then you can come up with a C to O ratio. And then we think that, you know, depending where you form in the disk, you might get a different C to O ratio compared to your star. So if you form beyond the water line, maybe your C to O ratio goes up in the actual planet. I want to caution you that when you're doing these spectra, there are a lot of different things that all change together. And so they're real degeneracies when you're trying to do spectroscopy. So imagine you went out and got, let's see right here, you went out and got a K-band spectrum of an exoplanet. It might be higher than normal because it's high metallicity, or it might be higher than normal because it's cloudy, or just because of its temperature. So if you really want to be able to measure these parameters with these low resolution spectra, these bulk parameters, you kind of need to have a pretty long band pass or a pretty wide pass band. So, you know, the temperature is less affected. It's sort of this 4 to 5 micron band than it is, you know, the clouds are more affected than the temperature. And so maybe that'll help you distinguish between what's going on at K-band. Okay. The next thing I'll say is about what you can do with higher resolution spectroscopy. So most of what I've talked about so far has been low and medium resolution spectroscopy. But if you can get up to high resolution spectroscopy, one of the things you can see is the Doppler broadening of lines. So as the object spins around, it Doppler broadens the line at about R of, say, 50,000 is a good number. You can measure the width of those lines, and that allows you to measure the V sin I, or the spin of the planets. And so Marta Bryan has done a lot of this, and she's been able to do it for younger objects and older objects. And you know what this shows is that the spins of exoplanets are pretty baked in at young ages. They don't vary a whole lot by the time you get up to a gig a year. If you can see when you're making these spin measurements, you might see that, you know, the blue shifted side of the line is a little bit darker, and then as it's going towards you, and then the red shifted side becomes a little bit darker as it's going away from you. And you can actually use that to make maps of exoplanets. So this is called Doppler imaging. Here, Ian Crossfield did it on a brown dwarf. This is the best example of this so far. But another thing you can do with high resolution spectroscopy of exoplanets. You can see exoplanets within disks, and that should be exciting to people at this conference. Oftentimes the star forming regions are far enough away that you need some pretty advanced techniques to be able to see really, really close in the exoplanets. And one of those is called aperture masking interferometry, which I'm happy to talk about more in questions. Here's an example of what you see if you take an image of PDS 70. So this is the disk, and then these are the two planets. Those two planets weren't circled. You might have a hard time picking them out. Are they clumps in the disk, or are they bona fide exoplanets? But what's really cool is that people have been able to verify planets by seeing them in accretion lines like H alpha. So in this case, the disk, you wouldn't expect to have H alpha emission. And so the fact that these two blobs really stand out compared to the disk in H alpha means that these are bona fide planets. So I think that's pretty cool. Okay, so here's what we can measure on these directly imaged planets so far. So we can measure the luminosity, the temperature, the surface gravity, which is kind of like mass, presence and properties of clouds, a lot of different things you can do once you can measure molecular abundances. You can measure the spin, you can measure 2D surface maps, you can see hydrogen accretion. In terms of results that specifically pertain to young stars, young planets. Young planets appear to retain their clouds at lower temperatures than brown dwarfs. Young planets appear to have more non-equilibrium chemistry and turbulent mixing than older brown dwarfs. The young planets seem to have similar spin to old brown dwarfs, although that plot didn't go out to very old brown dwarfs. And in star-forming regions, we've seen young planets that show mass accretion via H alpha. So that's all I have for this condensed talk. And I just wanted to point out that if you want to hear about the different instruments that you can use and techniques that you can use, there's more of that in the longer YouTube video. Thank you.
Thanks, Andy, for the great talk. One question from the Q&A says, which method would be more reliable for determining the formation mechanism, like gravitational instability versus core accretion for planets? Is it measuring the luminosity or temperature for young planets and comparing them to the evolutionary models? Or is it measuring elemental abundances for the planet and comparing them to the host star?
Personally, I think we're still in the all of the above stage. We just don't know enough about planet formation, and we haven't done this on enough planets to reliably be able to say, okay, this one is giving us a clear answer. So I think that may be a little bit of a cop-out, but I think that's still where we are in the field of exoplanet characterization.
Thank you. The next question says, how does one separate out degeneracies that you measure in the spectra?
Yeah, so here was my figure of degeneracies, and I think this is complicated but not impossible. The problem has been each of these exoplanets is so hard to study. Someone will come along with an H-band spectrum, and then someone else will come along with a K-band spectrum, and we try to stitch them together. We're going to do a lot better when we can do, if you can do 1 to 5 microns, you can kind of see that helps a lot with the clouds, right? Because if you can nail down the cloudiness at the longer wavelengths, then that tells you sort of a baseline for what to expect at the shorter wavelengths, and then you can see things like metallicity and C to O ratio. So I think the broad wavelength coverage is pretty important. And I think our first chance to really see that is going to come with James Webb, where we're going to have spectra that go from 1 to 28 microns. And you'll really be able to figure out, that will be sort of the first case where we know that we have enough data that is high enough fidelity that we can for sure distinguish between these major degeneracies.
The next question is, do we know why young planets hold onto their clouds better? And the next question kind of related is why non-equilibrium happens in the colder planets.
Yeah, so there's a nice theory paper by Mark Marley, 2012, that goes through a couple of these answers, and I'll try to give a short answer, but for a longer answer, I would look at that. I mean, essentially, the big difference that's happening between the young objects and the old objects, to first order, sorry, one up here. To first order, they have the same compositions, they have the same radii approximately. So what's different about them is their mass. And the way that the mass manifests itself onto the atmosphere is through surface gravity, because the scale height of an atmosphere has G in it, surface gravity in there. And so objects with lower surface gravity essentially have more material above the photosphere than objects that have higher surface gravity. And in terms of how much mixing you get, you can get more mixing in objects with, if you can mix over sort of a larger range of scale heights, that's easier to do with things that are low gravity that have bigger scale heights than things that are higher gravity. But overall, it's sort of a complicated concept, at least for me. And I think that 2012 paper by Mark Marley is a good place to look.
Okay, I think we're time to